going to talk about a bit about the optimization techniques, what we have done for making the proof recursion in linear and also in SNARK a bit more efficient. So I work on linear and I mostly work on SNARK. So SNARK is an end-to-end library written in Go for writing circuits which can be proven using SNARK proof systems. So you can write circuits, you can compile it into constraint systems, for example, R1CS, Blankish. Then you can run the trusted setup, particularly for the cross-16. You can use SNARK for proving using different arithmetization engines, so using CPUs, GPUs. And finally, you can use SNARK to verify the proofs. So we have the verifiers written in, for example, for the native verifier, for the mobile verifier. It's also possible to verify the proofs recursively in another SNARK. Or we can also compile a solidity verifier. So you can also verify SNARK proofs on chain, on Ethereum. So let's set the stage before we start. So what we want to do, let's say we have some kind of statement, which can be a mathematical statement or a computer program. And we have some inputs. We have the secret input and the public input. So the secret input is something what only the prover knows. The public input is known to everyone. So for as an example, what can be a statement? A statement can be something very simple. For example, I know the factorization of RSA primes. So I know two factors which multiply together result in some prime. And so, for example, I can prove that I know a solution to these RSA factorization challenges. And I can obtain the challenge money, but without revealing what are the particular inputs. Because like if I would reveal it, maybe like someone will front run me and they will try to get the money themselves. So what happens is that first we take the statement. We do like some kind of pre-computation on that. So we get some expanded statement, and then the prover runs this program. So for example, the prover gets some kind of execution trace. The prover proves using some technique, and we get a proof. And what we want to have usually is that the proof is short. What does it mean for the proof to be short? So the proof should be short in the sense of this expanded trace. So the steps, all the intermediate results of the computations. So, and if it is shorter, then it means that we have already won. So we have some like short proof of this computation. And we also want the verifier to be fast. So the verifier should run faster than running the computation itself, because otherwise, like, what's the point? And like complexity-wise, maybe we want that the proof and verifier work like it is, let's say, asymptotically faster. Maybe we want them to be, let's say, logarithmic in the size of the computation steps, or maybe like a square root. Or it will be very, very nice if it will be constant size. And optionally, we would like to have zero knowledge sometimes, but in a lot of applications, it's not necessary. So let's say some of the proving schemes. So there is the sum check, where essentially, if we represent the statement as a multilinear polynomial, and then the prover shows that let's say some property of this multilinear polynomial holds, and it doesn't require like some very fancy mathematics. It's like essentially we just evaluate polynomials. The problem with the sum check-based approach is that the verifier needs to do the final eval. So it means that the verifier needs to evaluate this sum check multilinear polynomial at some point. Then we have GKR, which is very similar to sum check. It's just layered. It's a bit more structured. We have STARKs, which are based on hash functions. So we can have some kind of polynomial constraints between like different steps and different columns. We have cross-16, which is one of the first pairing-based systems. And the nice thing about the cross-16 is that the proof size is constant, and also the verifier work is constant. But it requires a lot of pre-computation. It requires per circuit trusted setup. And finally, Blanc. Blanc is nicer in the sense that it doesn't require per circuit trusted setup, so it can use the universal trusted setup. There are, of course, a lot more, but I would say, like in the big picture, like these are like some nice examples. So let's say the issue is that for the first 3 schemes, they are very fast, and they do not require like any particular kind of assumptions. They only do finite field arithmetic and hashing, and no assumptions at all. So we just have to choose the hash function. But the proofs are not that short. So for the sum check, the proof size is logarithmic in the number of, let's say, in the number of steps. For STARKs, I think it's square root. So it is shorter, but not very short. So if the, let's say, if the statement, the input is huge, in like hundreds of millions of steps, then the proofs are still big. For the last 2, the issue is that the provers are slower because we use the fancy mathematics called pairings and KZG commitments. But the proofs are very, very short. So the proofs are, for example, like constant number of some group elements, and the verifier work is also very short. So like if we measure it concretely on a native machine, so it means that the verifier work is, for example, like milliseconds. Why we want the verifier work to be efficient and short is that when we go to L1, then it concretely means that we pay for less gas. So what should we do? We have fast provers, we have fast verifiers, we have slow provers, we have slow verifiers. So we can just combine like different approaches. Let's say we can combine the approaches because like one of the statements, what we can prove is the verifier implementation for the fast prover. So let's say if you have some very big statement, then we'll just use fast prover first. We get some proof, which is let's say not constant, but still smaller. Then we provide this as an input to the slower prover, but because the input is already sufficiently small, then the slower prover is actually also relatively fast, so we can run it nicely. And in the end, we get a very small proof, very fast verifier, and we can post this on Ethereum, and we are done. So we get best of the both worlds. We have the fast prover, we have the fast verifier, and we do not pay a lot of money. We don't pay a lot of money for verifying the proofs. We can use the like similar, let's say, combination techniques, CK pipeline combination techniques to compute the proofs in parallel. So let's say we have, in the context of rollup, we have a lot of blocks. So we can prove actually the blocks in parallel because even the fast provers, they are slow, so they take minutes. So we can actually run, let's say, up to like 400 proof generation in parallel, and then we can aggregate everything into a single aggregate proof, and we can post that on Ethereum. So this also gives us some additional saving in posting the proofs and in finalizing the L2 on Ethereum. So to summarize a bit, what different kinds of recursive proving we have to do. We have to do the PN254 block verification in PLS12377. It's for the pre-compiles. Then we verify the fast proofs, the vortex proofs in PLS12377 block. Then for the proof aggregation, we use the PLS12377 block proof verification in PW6761 block circuit. And finally, because Ethereum only supports the PN254 precompile, then we have to compress it back into some other curve, and for that we need to use the final approach. So what's the cost in verifying block proof? So there are the different steps. So first, we need to do some hashing to get the random challenges. We have some exponentiations where the exponent can be a variable or it can be a fixed value. We have scalar multiplications. And finally, the most complex part is computing the pairing. And pairing consists of 2 parts. So it consists of Miller loop and final exponentiation. And today's talk, we are focusing on the Miller loop and also final exponentiation. So, like, what can we optimize? So first, we work in elliptic curves. So what does it mean? So we have some base field. So we have coordinates which are defined over a base field. What we can think about it, essentially, they are like some integers modulo some prime number. And an elliptic curve is all of the solutions to some elliptic curve equation y, like y squared equals x cubed plus ax plus b. And so the elliptic curve is a solution to like this equation. So we have a lot of points, and there is also a scalar field. So let's say like if you fix a point on an elliptic curve, so like all the, let's say, all the multipliers of it, so they, if you have only a single, let's say, a single group in the elliptic curve, so they generate, like it generates like all of the points, and the scalars, they also, construct a finite field. So we have two fields. We have the base field, the points, and we have the scalar field for the scalars in the elliptic curve. It's really great if we have some kind of match. So right now we are thinking that we are verifying recursively, so we are verifying a Planck proof inside a Planck circuit. So all the arithmetic in a Planck circuit happens on the scalar field, but we need to do arithmetic in the base field, in the scalar field, so like in different fields. So we have some kind of mismatch. It would be really nice if we have a match somewhere. So the scalar field corresponds to the base field of some other curve. And there are, like, sometimes we have it, but most of the times we don't. So how can we fix it? We can just use multi-precision arithmetic. So we can do it like naively as for like in library. So we just split a big value into limbs. So for example, we split it into like 64-bit limbs. So if we do it like this, then when we think about the multiplication, then we essentially have to use the school book multiplication. And the school book multiplication, the asymptotic cost of it, it is quadratic in the number of limbs. So it's not super beneficial, or it's not super efficient. And also consider that we are only doing the integer multiplication. We also have to do the modular reduction, so we have to do it several times. So a bit more clever approach is actually to use the polynomial representation of these multi-precision integers. So it's the same, but we look at the polynomial where the coefficients are the limbs of this multi-precision integer. And in this case, because when we are creating a Planck proof, then like actually the prover can just hint some values, the prover can hint the result, and also the quotient, and then like we can check that this polynomial is equivalent at some random point. So when we compute the pairing, so the computations in a pairing happen in different groups. So they happen in the group of the points, but it also happens in the extension fields of the base field. So we have the G2, GT for the pairing, and so what are the extension fields? So essentially, extension fields are a field of polynomials where the coefficients are defined over the base field. And we also have to have like some let's say, fixed modulus, which is like some irreducible modulus, which essentially defines like how we can reduce values when they are bigger than the modulus. It's a bit simpler to look at the extension field elements as vectors, and then the multiplication. Multiplication inside the extension field. It's exactly as for the multi-precision integers, and we just do the modular reduction using the given modulus. We have the same problems for the extension multiplication. Is that the complexity is quadratic. So if you have high extensions, the 6th degree or 12th degree extensions, then it's just like very complex to compute. So what for optimization we can use like towers of extensions. So like instead of going to the 6th extension directly, we first go to the cubic extension, then we go to the quadratic extension, and then the multiplication becomes somewhat simpler. So as a concrete examples, let's see. Like if we consider a quadratic extension over a cubic extension, if we do a multiplication, then we need to do one, let's say, one cubic multiplication. Also for computing the result of the second limb in this 6th extension, we have to do 2 multiplications, cubic multiplications. But before we mode reduce, we can just add the polynomials, because like if you recall, then if you add polynomials, then the degree of the resulting polynomial, like, it doesn't decrease. It may actually, I'm sorry, if we add 2 polynomials, then the degree doesn't increase. It may actually like decrease if something cancels out. So there was a very nice result a year ago by Feltrud Prime, and he he actually showed that when we compute the extension multiplication, then we don't have to do it like using the towers. We can do it directly. And the idea is very simple. What we have for the non-native multiplication is that essentially we don't compute the value, but the prover provides the value using a hint, and also the quotient. Then the verifier provides some kind of challenge using Fiat-Chimera usually, and then we just check that this direct extension multiplication is correct. So this should be more efficient, and we wanted to figure it out. So we found the direct extensions, and we started to write out these equations, and we started to see like how beneficial it is for that. So the previous result was only for PN254. We wanted to implement also for the other curves, so for PWS6 761 and PLS12 377. Okay, let's write it out, and so we get something like this. So it looks something simple, but the issue is right now that all of these multiplications, what we have right here, they are non-native multiplications. So, like only for the left-hand side, like we see that we have at least one. So we have like 10 or 11 non-native multiplications. And if we do the non-native multiplication in this way that we provide the result using a hint, then we have to do a lot of range checking, and this is not like that efficient. So let's try to improve this approach a bit. And so actually, we can improve it like very simply, I would say. So when instead in non-native, if instead of the multiplication, we want to evaluate something more complex, some like let's say some multivariate evaluation, where like instead of multiplication, we have something let's say a times b plus c times d plus e times f and so on. So we have something more complex. Then we see that actually we don't need to compute all the intermediate results. So we only need to know what is the full result of this multivariate evaluation. And the complexity stays the same regardless if we do non-native multiplication only, or if we do this more complex multivariate evaluation. And if we implement it this way, then actually like evaluating these extension polynomials, like it becomes a lot more easier. So let's now write it out again, like in full. So we have the A, B, C, and N and P. So what we do, at least in SNARK, is that we do not evaluate non-native and extension multiplication directly. We just write it down that we need to evaluate them later on, and we only provide the result using a hint. Because this allows us to share some of the computations. So for example, if we, instead of computing a Fiat-Chimera challenge for every check, we compute it over all checks, like if we Fiat-Chimera or we hash all of the inputs, then we can share this random variable Z. We can compute all of the powers of Z. We evaluate the P of B at this one place because it is shared over all checks. We evaluate A and B. And now we check. So we replace this A part, the B part, and also the P part. And now we have like this one big thing, what we need to evaluate. But this is let's say something what we can evaluate with the non-native operation, which corresponds to a single non-native multiplication. And if we count it, so on average, let's say if we amortize the P part, then we actually only have like non-native operations, and this is very efficient. So for evaluating the extension multiplication, we only need 3 non-native operations. And the main cost here is checking the range checking the hinted values. So actually doing the multiplications themselves, it's cheap, but it's just like when we work in 64-bit limbs, then we have to check them. When we look at the benchmark results, so this is the number of constraints in Plonkish. So on average, we were able to get 40% reduction. But there are like still some ideas what we have for improving the performance. So like one of the things to notice is that we don't need to actually find every quotient. just need to like know that there is a quotient. So if you look at the random linear combination, then we can also provide a single quotient. And we can apply it also for the like different operations, and we can also apply the same technique for different curves. Thank you.
Thank you, Ivo, for the presentation. It was nice. Are you ready for some Q&A?
Yes.
So let's look at the questions. Why do you need 4 different combinations of Planck in Planck?
Yeah, it's a very good question. I ask it myself like many times. So we need it because we are like on one hand we are restricted to what we already have. So for example, if we want to verify a Planck proof on Ethereum, then we can only use BN254 because this is the only precompile which is provided by Ethereum. And otherwise, if you would like compute a pairing using let's say an assembly implementation, it will be just expensive. For proof aggregation, we would need to have, let's say, a chain of or let's say 2 chain of curves where like the scalar field of one curve corresponds to the base field of the other curve, and they don't come like that often. So we have to particularly construct them. And for example, because BN254 is already given, we cannot construct a 2 chain for that. So we also had like some other like other way, because in linear, for example, we have to prove also like pairings. So let's say like if someone calls a pairing precompile on linear, then we have to prove it that like we have computed correctly. So we have to show BN254 precompile, but let's say the curve we are working in is PLS12377 for aggregation reasons. So it's just is what it is.
Makes sense. So next question, can you show the benchmarks again?
Yes.
Actually, we have like a technical issue.
I'm sorry.
You can only show the questions at the end.
Yeah.
But you can take the questions offline with Ivo after his talk. So the next question, does it work inside Nova folding step?
It's a good question. Unfortunately, I cannot answer it. Probably. I think it probably would. But I do not know the techniques exactly to answer it concretely.
Next question is, how do you generate randomness in circuits?
Okay, that's a very good question, and actually, like this is one of the nice improvements what we have. So for Planck, what we do is that we don't use vanilla Planck. We use like a variation of Planck, where if we want to, let's say, hash some variable inside the Planck circuit, then we like copy this variable into this another column of of Planck. So we have a different one more column, and then essentially we use the commitment to that column as the random value.
So we don't see the next question, but I can read it from the phone. Can you use Karatsuba for direct multiplication instead of schoolbook? I think
Yes.
it's for the extension, maybe.
Yeah, we can. And actually, like this is how we did things before, yeah.
And I believe it's going to be some more optimizations than compared to the benchmarks.
Yep.
And what if we take the next question?
There's one more.
Can you use this technique to anything that can be expressed as polynomials? I think you explained that for multiplications.
Yeah, we can do it. So we have a plan to also use it for, let's say, elliptic curve operations, so for additions, doublings, scalar multiplications, and we also already expect for it to give like a lot of performance improvements.
And we have one final question. It says, can we use the same non-native field arithmetic mechanisms to prove SECP256K1 operations in BN254 scalar field?
Yes, we can. So we prove SECP in PLS12377. So on linear again, we also have to prove the ECDSA precompiles, and so yeah, we can do it. We can do it fairly efficiently, I would say. And like for us, because all of the methods or all of the techniques what we use, like they are very generic, so we can use the field what we emulate and the field what we work in. So everything's generic, and it will work very well.
With respect to this question, it means it's already implemented?
Yes, so it is implemented. You can just take it as is.
Okay.